In this video, we will write an additional project and practice working with the model, .stream, and element files. I remind you that you can familiarize yourself with the structure of the files in our mini-course, which is located in the same playlist. Alternatively, you can locate the necessary details in the instructional manual that is provided. The project is named Tool Charges Plates. In the project, we will describe the following. A proton and an electron enter with some initial velocity into a uniform electric field between two charged plates. Particles enter parallel to the plates at a certain distance from each of them. From the side of the electric field, the particles will experience an electric force that alters their trajectory. Let's move on to describing the files. First, let's describe the file model. Here we need to describe the movement and characteristics of a proton and an electron. Let's begin. First, let's describe the setup of global. In our project, there are two objects and one electric field. Let's set the appropriate parameters. Leave the remaining fields empty. Now let's describe the objects. Start with a proton. We'll set the name, charge, and mass. Let's set arbitrary initial coordinates. Also, let's set the initial velocity of the proton between two plates. We will keep the velocity along the y and z axis 0. The object has a unit radius. We will not specify the texture. By default, it will be rendered as a sphere-shaped object with a smooth surface. Let's establish the color as red. Establish the color field as 255, 0, 0. We will configure the type as classical, as we require sections like mechanics and electrodynamics for our needs and objectives. Our object will not emit radiation, so let's set N. Display the object's track for a clear visualization of force and velocity vectors. We won't display the name to avoid cluttering the drawing. By analogy, let's describe the electron. We will set the charge to be equal to -1, named E, and set the initial y coordinate to be -3 to prevent the proton and electron from merging in the model. And each was visible. Set color to blue, 0, 0, 255. Leave other fields for proton. We will retain the remaining fields in their current state. Now let's describe the electric field. We'll set up the Cartesian coordinate system. And initial coordinates are set to 0. We will set the forces along the x and y axis to 0. Along the z axis, we will set a force and limit its action with the following coordinates. Well, there you go. I have nothing more to add. That's all I wanted to say. Thank you for listening. The complete collection of all things, encompassing each and every aspect in detail, without any exceptions or exclusions. Please specify the type of field E. Let's define the space in the space setting. For time-saving purposes, I described it off-screen. Now I will explain the meaning of each parameter. Let's choose the integration step and the solution method. Collision parameters will be deactivated. We will proceed to set the speed of the animation. Allow us to establish a scale for the X, Y, and Z axes in order to accurately measure and represent the data. These parameters will be set to 0. We won't need them. We are not working with a two-dimensional coordinate system. The scale of the background is currently set to 10. The position is set at the origin point. Let's arbitrarily position the camera. The camera is of type orthographic, meaning it has a fixed perspective. The flag of axis will be deactivated. We need to choose a color to be applied to them for customization purposes. The flag indicating the presence of a grid will also be turned off and deactivated, ceasing its display on the screen. Let us activate speed flags and adjust the scale to 100. We will perform the identical action with force vectors, albeit modifying the scale. Let us configure the ultimate parameter to a value of 0. Next, the box parameters. Let's set any. Collisions won't be needed. The switch and draw parameters will be disabled and turned off during the operation process for enhanced efficiency and accuracy. Let's set up the graph. For this, we will write plot. Let's label the axes. Let's consider the position of particles on the graph along the X and Z axes. To ensure accurate visualization, let's set the scale of the axes to -1 and 10 for correct display of the graph. Center the axis for positioning. Continued. Subtitles created by Dimotorzok. Ensure that the color of the axes is set to white. Let's analyze the model that has been obtained. To do this, let's save the file and relocate it to Alaska for further examination and evaluation. Press the Start button to initiate the process. Take note of the presence of two objects, namely vectors of force and velocity. Additionally, observe that the graph has been opened in a separate window for visual representation and analysis purposes. Next, we'll move on to describing the .stream file. We need to describe the electric field between the plates. Here is also a global setting. In this setting, you need to set one segment and one disk. Using them, we will show the intensity. We will set the rest of the parameters to 0. Let's provide a description for the segment. Let's assign the name I to it and set the field type as I. That is the electric field. Then we'll set coordinates. I'm as blue as the ocean. You're as blue as the vast sky. All these blues. I don't know why I had high hopes. Why? Why were we feeling like we can't bear the weather tonight? We cannot tolerate the weather tonight. The quantity of lines will be equal to 1. Let us set the tolerance parameter as follows. Let the segments be spaced at intervals of 5 units, with the number of segments being equal to 2. Let's set the color to gray. This is 155, 155, 155. We will display the segment name. In order to assign a direction to our hypothetical stress vector, let us provide a description of the disk setup. We intend to retain the same name and type for the field in question. In order to show as a cone, we need to configure the following parameters. For correct display, we need the interval and number of segments of the disk to match the interval and number of segments of our segment. We will maintain the color as is, matching it to the tolerance of the fields without incorporating any angles or lines in the final output. The display will be activated and turned on to provide visual output for the user to view and interact with. Let us have a look at the project that resulted from our efforts. We are able to visually perceive stress lines and 2 objects undergoing the curing process, as they are described in the .module file. Finally, let's describe our plates in the .element file. To accomplish this, in the global setting, we will set 2. Boxes are currently present. Let's proceed to their description. The length and neck plates will be the same as 100 units of measurement. Thickness 1 unit of measurement. The position of the center on the axis will be 0, 0, and -10. We will refrain from rotating the plates, thus we set zeros in the parameters designated for rotation. The color of the plate is red, and its transparency is nearly equal to 1. This is done in order to ensure that when the camera rotates, we are still able to see our particles even when they are positioned between the plates. Using analogy as a guide, let us now provide a description of the second plate. We made changes to the position of the center along the z-axis and adjusted the color to blue. Furthermore, it is necessary to move the files we previously described to the state of Alaska.
And proceed to press the Start button. As we can clearly see, our project is fully prepared and ready to be initiated.